All right, let's get right into it. What if I told you there's a way to check if two massive chunks of text are identical in a single, instantaneous step? I know, it sounds like some kind of programming magic, but it's totally real. It's called string hashing, and it is an incredibly powerful algorithm that will completely change the way you think about working with text.
I mean, really think about it. You're trying to find one specific line in a log file that's gigabytes in size. Or maybe you're searching for duplicate code across a huge project. The normal brute force way is just painfully slow. But what if you could do it, bang, almost instantly? How is that even possible?
Well, the answer is string hashing. It gives us what is basically the holy grail of efficiency in computer science, O1 or constant time substring comparison. Now what that means is, after a little bit of prep work, the time it takes to compare two substrings has nothing to do with how long they are. Seriously, comparing a 10-character string takes the exact same tiny amount of time as comparing a 10,000-character string. It's wild.
And that right there, that's the constant time promise. It really is a superpower for your algorithms. We're about to unpack how this lets us check any two substrings for equality in just a single operation.
Okay, so this superpower isn't completely free. There is a small, one-time, upfront cost. We have to pre-process the entire string first, and that takes O of n, or linear time. All this means is we have to look at every single character in our string exactly once to build up the tools we need.
But here's the thing. After you pay that one-time ON cost, the payoff is just immense. Every single substring comparison you do from that point forward is O1, lightning fast. You can do 1, 10, a million comparisons. It doesn't matter. They're all basically instant. It's a classic trade-off. Do a little bit of work now for incredible speed later.
So how does this magic actually work under the hood? Well, we're essentially going to turn our strings into numbers using a technique called the polynomial rolling hash. Now that sounds super complex, I know, but I promise you, the core idea is surprisingly simple and really elegant.
Think of it like a recipe. First, we just turn every character into a number, like its ASCII value. Easy enough. Then we pick two special numbers, a base, b, and a really large prime number called a modulus, m. The modulus just acts like a bucket to keep our final number from getting astronomically huge. Finally, we treat the string like it's a number in a different base, and that gives us our unique hash value.
Now, the rolling part is where the real genius comes in. It means if we already have the hash for the word apple, we can figure out the hash for Piplet in constant time. We don't have to recalculate everything from scratch. We just mathematically subtract the value of the first character, a, shift everything over, and then add the value of the new character, t. That's the rolling magic that makes it so fast.
Okay, theory is great, but where do you actually use this thing? Let's look at some powerful, practical applications where this technique really shines, especially in coding interviews and real-world software development. The most famous application by far is the Rabin-Karp algorithm. So instead of slowly comparing a pattern to a text character by character, Rabin-Karp is way smarter. It just calculates the hash of the pattern it's looking for. Then, it rolls a window of the same size across the text, just comparing hash numbers at each step. And just look at this performance jump. A naive search is O of n times m, which can be absolutely disastrously slow on large texts. Rabin-Karp brings that down to an expected time of O of n plus m, a linear runtime. For text processing, that is a total game changer. But wait, it gets even more clever. We can use the exact same hashing principle for something that seems totally different, like instantly checking if any part of a string is a palindrome, reads the same forwards and backwards. The solution here is just so elegant. What you do is you pre-calculate the rolling hashes for your original string, and you also do it for a reversed copy of the string. Then, to check if any substring is a palindrome, you just grab its forward hash and the corresponding hash from the reversed version. If those two numbers match, boom, you've got a palindrome. And again, that check is an O of 1 operation. So far, this whole thing seems almost too good to be true, right? Well, there is one crucial weakness, one major caveat that we absolutely have to talk about, especially if you're in an interview. We need to talk about collisions. This is the key question. A hash collision is when two totally different strings, just by pure random chance, end up with the exact same hash number. Now, if we blindly trust that hash, we might think the strings are equal when they're actually not. So, how do we deal with that? First, let's bust a few common myths. Myth 1. Collisions never happen. Wrong. They're rare if you pick good numbers, but they are always possible.
Myth 2. Any old base or modulus will work. Nope, bad choices can make collisions way more likely. And a big one, do not, under any circumstances, use the language's built-in string hash for this. In Python, for example, it's salted, which means it changes every time you run the program. It's not stable.
So, what's the pro move? How do we make our hashing robust enough for applications where correctness is critical? Well, the professional standard is a technique called double hashing.
And double hashing is pretty much exactly what it sounds like. We run our entire hashing process twice, in parallel, but using two different large prime moduli. For two strings to be considered a match, both of their hashes have to be equal. The chance of a random collision on one hash is already small, but the probability of a collision on both independent hashes at the same time becomes so infinitesimally tiny that it's just negligible in practice.
All right, let's pull all of this together into your final takeaway. This is the interview-ready summary you'll want to have in your back pocket for any technical discussion.
This table really gives you the strategic overview. You want to use rolling hash when you expect to make lots of substring queries or for things like palindrome checks. For a single, guaranteed correct pattern search, something like KMP is a great choice. But where rolling hash really wins is on its versatility and, honestly, being way simpler to code. So, let's sum it all up. 1. String hashing gives you those sweet O of 1 substring checks after an ON setup. 2. It's the engine that powers the super-fast Rabin-Karp search algorithm. 3. Collisions are a thing, but we can make them a non-issue with good parameters and double hashing. And 4, it's often your most flexible and easy-to-implement tool in the entire string algorithm toolbox.
And that brings me to one final thought for you. We've just seen how to check if any two substrings are equal in constant time, which is amazing for finding duplicates. But how would you take this powerful new tool and use it to solve an even harder problem, finding the longest duplicate substring inside a single piece of text? I'll let you think about that one. The answer actually combines hashing with another classic algorithm.